Okay, so this one, number 8, is trying to find the equations of the tangent lines to this curve, x times y equals 32, if the tangents are perpendicular to another given line. So it's all about like the tangent, right? The slope of the tangent. So now we need to find the slope of this line and also the slope that is perpendicular to this line. So the best way to do is to rewrite this equation in the slope intercept form. Okay, so we have 2y equals x plus 6, and y is equal to x over 2 plus 3. So from this equation, the straight line, we know that the slope is equal to 1/2. So that makes the perpendicular slope of this line would be -2. Okay, just remember all the perpendicular lines have slopes that are negative reciprocal of each other. Okay, all right. So now we know that this is the slope of the tangent line. So now we need to like look at the equation of the curve. So x times y equals 32. So you know that you're going to find the derivative of this function. So if that is possible, if you don't want to use the product rule, then you can easily just isolate the y from this equation, right, from the left-hand side. So y is equal to 32 divided by x, okay, which is also equals to 32 times x to the power of -1. Okay, so we can easily find this, the dy dx, okay, using the power rule, right? -32 times x to the power of -2. So that means like -32 divided by x squared. Okay, and now we know that the slope of the tangent line must be equal to -2. So that means I'm going to solve for x, okay, by making the slope equals to -2, like that. All right, so now we can solve for x squared, cross multiplying the x squared to the other side, and then we have 32 divided by 2 is 16, and that means x is equal to plus or minus 4. All right, so now we have to go back to look at if the point at the point of tangency at x equals -4, what is the y coordinate of this point? So you use the original function, y equals 32 divided by x. So when x is -4, that means the y value is equal to -8. Okay, so we have the one point where you can draw the tangent line with the slope of -2, or when x is 4, then we know that the second point would be 8. Okay, so easily you're going to write down the equations of the tangent line required in this problem. Okay, so the first one, y minus -8 equals the slope times x minus -4. So that's one of the tangent line. The second tangent line would be y minus 8 equals -2 times x minus 4. Okay, so this is a basic problem. Okay, yeah, that's all right, Isabella. You're good. All right, I will get you for the attendance. Tochi is also here. Yeah, that's good. So we are on the question number 8, okay? All right, so the chapter 3, it's about the related rates problem. Okay, let's start with something straightforward first. So this is the particle motion problem. So the motion of a particle is described by this position function. So this position function is just a polynomial cubic function where t is greater than or equal to 0, s is measured in meters, and t in seconds. So to find the average velocity from 3 seconds to 5 seconds, we know that average velocity is the same as finding the slope of a secant line, right? So we are going to find s of 5 minus s of 3 divided by 5 minus 3. Okay, so this is more like the delta S divided by the delta T. Okay, so that gives you the average velocity. Okay, so you can use your calculator, figure out what is the value of S of 5. So S of 5, I have equals to 25. and then s of 3, it's equal to 5. So then divided by 2. Okay, so that gives you 20 divided by 2 is 10. And then don't forget to write down the limit, the units. All right, so that would be the average of velocity of this particle on that time interval. Okay, now on the AP exam, like I said, if this is a 2 marks question, they are looking for the first mark based on you actually shows this expression. Okay, 25 minus 5 and then divided by 2. So when you think about like entering this response using your keyboard, you can say, okay, I'm finding the average velocity, and that is equal to, so open a bracket for 25 minus 5 and then divided by 2, and that is equal to 10 meters per second. So the first mark goes to this expression. That's worth 1 check mark. And then the second check mark is the correct, you include the correct units. Okay, so the final, like the numeric answer, is not a big deal, right? So usually you can leave your answer without simplifying. The number is still okay as long as you have the right the correct number put into the formula. Then even though you don't simplify the numbers for your final answer, you still get the first mark. Okay, and then the second mark will be based on the correct units. That makes sense? Okay. Now, so let's go back to this part B. What is the acceleration at 5 seconds? So we know that the acceleration is talking about the second derivative of the position function. So right away, you write down the velocity function would be 3t squared plus 12t plus 9. And then the acceleration function, it's continue to take the derivative of the velocity function. That's 6t minus 12. Okay, so to find the acceleration at 5, so you put a of 5, it's equal to 6 times 5, and then minus 12. So that would be 30 minus 12, that's 18 unit meter per second square. Okay, so on the AP exam, how do you like type the square? You can do 18 meters slash s, this symbol, square. Okay, this triangle symbol, just like the button, the triangle button that you find on your graphing calculator keypad. Okay, that makes sense. All right. Now, how about when is the particle at rest? So we know that when the particle is at rest, that means you're looking for what is the time when the velocity is equal to 0. Okay, so that's easy. I just look at this velocity function, and we are going to make it equal to 0. Okay, so this is v of t, and you're making it equal to 0. So you can either reduce it by 3 or just simply factor it out. And then continue to factor this trinomial. 3 and 1, negative, negative. So that means t, it's equal to 1 second, or t equals to 3 seconds. So that would be your answer. Okay? All right. So how about the time when is the particle's velocity decreasing? So this one, you think about when the velocity is decreasing, that means the acceleration is negative. Am I right? So velocity decreasing. Okay. When the acceleration, it's negative. So now you have the direction, what to look for. So you need to look for when is the acceleration negative. So the acceleration function is a of t equals 6t minus 12, and you're going to make it negative less than 0. Okay, so you're looking for when t 60 taken out from this two terms, you have, okay, 6 times t minus 2 is less than 0. So you understand that the only possible to have a negative acceleration is when t is less than 2. Okay, but think about time cannot be a negative number. So in no time, you see that we have to bound the time uh, at the lower bound at 0, but up to 2 seconds. Okay, so t must be in between 0 second up to 2 seconds so that the acceleration would be negative. That makes sense? Okay. All right. So now the next question is the related rates problem. Okay, so this is a simple one. So let's start with that. So the size of an equilateral triangle increases at a rate of 4 centimeters per second. So at what rate is the area increasing when the area is 300 centimeters square? Okay, so let's draw the diagram. So we're looking at an equilateral triangle. Equilateral triangle means all three sides are the same and each angles are equal, right? All three angles are the same with the measure of pi over 3, 60 degrees. Okay, so now we know that we are trying to find, like we're given the rate of the size, right? So you label the size of this equilateral triangle as x. So we are given the rate dx dt. It's equal to positive centimeters per second because you're given that the x value, the size of this triangle, it's increasing. So you're looking at a positive rate. Okay. And then what we're trying to find is to find the dA, the area. How fast is the area changing? That's your target rate. And then the snapshot moment would be when the area is exactly 300 centimeters square. So this is the snapshot moment. Okay. So a question like this is very simple. You are looking at the target rate. So that means you have to find the equation representing the area of this triangle. So this triangle, the area, I need to know the height of this triangle. All right, so let's look at the height. So based on this triangle, we can only find the expression for height using the sine ratio. So let's set up the sine ratio. Sine pi over 3, it's equal to the opposite side over the hypotenuse. Okay, so we can easily like figure out x is equal to x times the sine pi over 3. And sine pi over 3 is square root 3 over 2. Okay, so this is the expression in terms of x for the height of this triangle. So now we go back to look at the quantity equation for the area. All right, so area of this triangle would be 1/2 times the base times the height. Okay, like this. So simplify it before you differentiate it. Okay, so we have the coefficient square root 3 over 4 times s squared. So simple function, and now we're going to find the dA, okay, differentiate it with respect to time. So dA dt would be square root 3 over 4 times 2x times dx dt. Okay, so dA dt is the target rate, and then this is given 4 centimeters per second, and now we don't know the x value at the snapshot moment. So on the side, you have to find the x value when the area of the triangle is 300. So you just calculate for the x, okay, using this area function, right? So that would be root 3 over 4 times s squared equals 300. Okay. So now we have the x squared equals 4 times 300 divided by the square root of 3. Okay, so when I try to rationalize it, then you can easily simplify it the 3 in the denominator cancel with the 300. So we have 400 square root 3. That is the s square. Okay, and of course we know that the x must be greater than 0. So we're looking for the positive square roots of this number. So this is like a nested square root. So we have the 20 times 3 to the power of 1 over 4. So this is the x. Okay. All right. So now I guess you know what to do. You're going to sub in all the information back into this derivative function. So dA dt it's equal to, so cancel the 2, reduce it. We have square root of 3 over 2 times 20 times 3 to the power of 1 over 4, and then times 4, okay, which is the dx dt. So simplify everything. That's 10, that's 40. And then square root 3 times the fourth root of 3. That would be 40. Let's say 3 to the power of 1/2 times 3 to the power of 1 over 4. So we can combine the two powers, the two exponent. That would be 3 to the power of 3 over 4. Okay, so that is the dA dt. Okay, and again, don't forget the unit. The unit for this value is the dA dt would be centimeters square per second. Okay. All right. Okay, so this is a very typical related rates problem, a simple one. Okay, number 11. So a floodlight is positioned on the ground shining on the wall that is 10 meters away. So let's draw the diagram. So let's say this is the floodlight, okay, on the ground, and which is 10 meters from the wall. Okay, and then a woman 1.7 meters tall starts at the wall and walks toward the light at the rate of 1.2 meters per second. So let's say the woman is walking from this point going in this direction. So at some point she's standing right here, and the height of this woman is 1.7 meters. Okay, and now we want to find how fast is the height of her shadow, okay, on the wall increasing when she is 2.5 meters from the light. Okay, so if I let x be the distance between the woman and the light, then this will become the snapshot moment. Okay, and then now when you draw this diagram with the two similar triangles here, then you can think about, oh, what do I need? I have one variable, and I also need a variable to represent the height of the shadow shine on the wall. So let's say y represents the height of the shadow on the wall. Okay, so now let's write down what do we know. So what we are given that the dx dt. Do we know the dx dt? So the dx dt is talking about like related to the rate of the walking rate of the woman. So now at this point, if I label the x representing the woman, the distance between the woman and the floodlight, can you tell me if the woman is walking toward the light, is the dx dt going to be positive rate or negative rate? Is the x value increasing or decreasing? It's decreasing. Okay, so the x value is decreasing. So this is a very important carefully. You have to carefully determine the correct sign of the rate. And this rate depends on how you label the variable. Okay, so if I label the x representing the distance between the woman and the floodlight, then the x value gets like shorter and shorter, okay, over the time. So this is important, all right? Make sure that you're getting the right sign of the dx dt, all right? And now what we're trying to find is we are trying to find the dy dt. okay, at this snapshot moment. So usually when you see a similar triangle, a triangle like set up like this, then think about the similar triangles. All right, for any similar triangles, we know that the corresponding sides, okay, are proportional. So we're going to set up like based on the big one, the big triangle, y over the small one. Okay, so this length here to this length, y over 1.7, it's equal to the entire another side of the big triangle, which is 10 meters, compared to the small one, which is x, like that. Okay, so you're setting up this equation based on the direct proportional of the corresponding size. Okay, now we can easily just cross multiply these two numbers. So we have y equals 17 over x. Okay, so this is a simple quantity equation, and we can easily just like find the derivative of this function with respect to the time. Okay, so we have dy dt equals to negative 17 over x squared times dx dt. So always keep in mind this is the related rates function. All right. So each variable is changing over the time. So when you differentiate it, you have to think about we're differentiated with respect to time. Okay. All right. So this one is simple because we don't need to calculate any other information. So we already have the snapshot moment to be plugged into this x squared. So dy dt is equal to negative 17 times 2.5 square and then times negative 1.2. Okay, so that would be giving the final answer like in decimal form, 3.264 meters per second. Okay, that makes sense. And you can see that this is a positive rate, right? A positive rate. So that means the shadow is supposed to be increasing. And you can imagine that, yeah, that's correct. If the woman is standing more closer to the floodlight, then the shadow shine on the wall, it's going to be longer, right? Depends on like at what point the woman is standing, right? So the y value is increasing. So that makes sense. You're getting a positive rate for the y value. Okay. All right. Okay, so one more question on this related rates problem. So at 1 p.m., the ship A was 100 kilometers south of ship B. So let's draw. This is B, and we have another ship that's A down here. Okay, it's 100 kilometers apart. All right, ship A travels north at 40 kilometers per hour, and ship B is sailing east. So ship B is sailing in this direction, and A is sailing north, okay, at the speed of 40 kilometers per hour. So how fast is the distance between them changing at 3 p.m.? So at some point after 2 hours, they are right here. Okay, I'm going to draw this triangle like a simple one, like a right angle triangle. So in this case, first of all, we know that from time equals 1 p.m. to time equals 3 p.m. So we are looking at the snapshot moment after like at 2 hours, after 2 hours. Okay, we want to know like after 2 hours, like what is exactly the distance between the two ships are changing at that moment. Okay, now if I think about this is a right angle triangle, I'm going to let's say x and y be the distance of the ship A and B traveling. Okay, all right. So in this case, I want to find the z. Okay, so that represents how fast they are, the distance between the two ships are changing. All right. Now, first of all, let me write down the given rate. So what do we know about the dy dt? So dy dt is talking about the speed, how fast the ship A is it's traveling. So what is the speed of the ship A? Ship A is traveling at 40 kilometers per hour. So does it mean that dy dt has a positive rate? So it all depends on how I define the variable y. Okay, so this is very important. So if I think about y is the distance between the ship A from ship B, like this point, then because the ship A is traveling north, so that means the y value is actually decreasing. Okay, so you have to be careful that dy dt should be negative. Okay, 40 kilometers per hour. Okay, but the dx dt, and x represents the distance that the ship B is traveling to the east, right? Um, so that means the x value actually increases. So we're looking at a positive rate, okay, for the ship B. Does it make sense? Okay, so once you have this given rate put down, and then now your target rate is to find what is dz dt equal to after 2 hours. All right, so go back to look at this triangle. This is a simple right angle triangle. So definitely you guys will want to use the Pythagorean theorem to relate all three variables, okay, in this equation. And then we are going to differentiate it implicitly with respect to time. Okay, so we have 2x dx dt plus 2y times dy dt equals 2z times dz dt. All right, so we can cancel the 2, reduce the entire equation by 2. And then now let's think about, we have dx dt, we have dy dt, and we're trying to find the dz dt, but still we don't know what is x and y and z at that moment, right? At time equals 2 seconds. So we need to calculate these information, all right, on the side. So let's say at t equals 2 hours. So think about x is the distance that the ship B has traveled. So we know that the speed of the ship B is 30 kilometers per hour. So in 2 hours, ship B has traveled for 60 kilometers. Okay, so time, the distance is equal to the speed times the time. All right. So that is the x value. What about the y value? Now the y value is a little bit tricky. We know that originally the ship A is 100 kilometers away from this point B, but now the y value is moving toward the point B. So that means the y value is going to be 100 minus 2 times 40. That is only 20 kilometers. So that means the y value is talking about, this is only like 20 kilometers after 2 hours. Okay? Does it make sense? All right. Now the z. So finding the z value, we have to go back to use this Pythagorean theorem. So we know that the z square is talking about the square root of the x square, which is 60 square plus the 20 square. Okay? So this number, you can do it on your calculator, 60 square plus 20 square. Okay, that would be square root of 4,000. Okay, and this number is not a perfect square, so don't mess up. So 4,000 is not a perfect square. So this will be roughly like 63.245, like that. Okay, so now we have all this information that we can plug it in. So 60 is the x value, and then dx dt is positive 30 times y is 20, and then times negative 40 equals to 63.245 times dz dt. Okay, or sometimes you can keep this as an exact value. Okay, so you can easily find dz dt by manipulating the term. So to save the time, I just give you the answer, right? So this is equal to 15.8 rounded to the nearest tenth kilometers per hour. Are we okay with this kind of a problem? So Feng is asking, can I define y as the distance a travel? A? Yeah? So yeah, you can define the y as like the distance a travel. So then you have to always think about 100 minus y. Okay, when you like set up the this equation using the Pythagorean theorem. That makes sense. So your diagram would be like drawing differently. So let's say this is the original point. So this is 100. Okay, and this is B, A. All right. So at some point after 2 hours, let's say the A is right here. Okay, if you think about this is actually the Y, the distance that the ship A has traveled, then when you set up the equation using the Pythagorean theorem, then this length here would be 100 minus y, and this is still an x. That makes sense? Yeah. So it's perfectly fine, but then I think it would be a little bit easier when you like set it up like this x squared plus y squared equals z squared. It makes it a little bit easier to differentiate it. Okay, but that's okay. No matter how you set up the equation, you base on your diagram. Okay. All right. So number 4, chapter 4 is about the extremer, which is talking about the finding the absolute maximum, minimum, or the local maximum or minimum problem. Okay. Now the first one, number 13, is finding the maximum value of the function f of x, which is defined on a closed interval. Okay, closed interval. So in this case, always think about whenever you're trying to find the maximum value, we refer to finding the absolute maximum value. Okay, on this domain, on this closed interval. So you understand that we have to find the critical number because the absolute maximum only occur either at the endpoints or at the critical number. So we have to find the critical number of this function. So quickly find the derivative. Okay, you can factor out the 6 from each term. Okay, so the critical number would be at x equals 1 and 2. And remember, this original function is a polynomial function. There's no restriction. And you also want to make sure that the critical number occurs within the domain. So make sure that these two numbers are in the domain, okay, in the closed interval. Okay, and now we are going to like just simply check the function value at the critical number and at the endpoint. So let's say this is the x value, and this is the function value f of x. So we have the lower bound at -1, and then we have the critical number at 1, and also another the right bound of the interval at 2. Okay. So you just quickly calculate what is the function value at each x value. Okay, when x is -1, the function value is -24. When x is 1, f of 1, it's 4. When x is 2, then the function has the value of 3. So it looks like we're looking for the absolute maximum. This is the absolute maximum. Okay, at the point 1 and 4. Okay, so this is how usually how we find the absolute maximum or the absolute minimum of a function defined on a closed interval. Okay, all right. Now, number 14, similar problem, but then this one is talking about finding the critical numbers and the intervals of the increase and decrease of a rational function. Okay, so whenever you have a rational function, always take a look at the non-permissible value or the domain. So we know that in this case, x cannot be -2 because this one will result in a vertical asymptote, okay, at x equals -2. All right, now let's find the critical number by finding the first derivative. So y equals x squared over x plus 2. So using the quotient rule, so y prime, okay, low d high minus high d low would be 1, and then all divided by the low square, like this. Okay, and then simplified it. Okay, multiply out the two brackets. We have 2x squared minus 1x squared, that would be 1x squared, and then plus 4x. Okay, and then divided by x plus 2 all squared. So factor out the 1x from the numerator. Okay, so this is the derivative of this given function. Now, so the critical number here, look for the 0 in each factor, okay, in the numerator. So the first critical number would be when x is equal to 0, okay, and then the second one would be x equals -4. Okay, so make sure that you're not looking at the non-permissible value. All right, so we have two critical numbers of this function. Now, to find the interval of increase and decrease, we have to use the first derivative test. So in other words, you're going to set up the sign chart, okay, for all these values. Now, in this case, we know that we have two critical numbers, but then when you set up the sign chart, you also want to include the -2. And you know that the -2 is kind of like a significant number. It's a non-permissible value. All right, so when you check the intervals of increase or decrease, you want to include this non-permissible value in your chart. Okay, so set it up like this. Okay, oops. All right, so now let's look at this function. So we need to check the x, the sign of the factor of each factor. So we have x and then x plus 4. And then the last one, it's just like the square. So we know that no matter what number we put it in, oh, I need to leave one more space here. Okay, so this is -4. So the test point. Okay, so this is x plus 4. And then the denominator, you don't actually need to check it because you know that whatever the x value we put in, the square of any number is going to be all positive, right? So let's write down the test point. So the test point in each interval, let's say x equals -5, x equals -3, x equals -1, and x equals 1. Okay, so when x, checking the sign of the factor x, that's negative, 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 positive. And then the second factor, -5 plus 4 is negative, positive, positive, and positive. So that means the y prime, it's positive, negative, negative, and positive. So that means the function y itself, it's increasing, decreasing, decreasing, and increasing. Okay? That makes sense? So if you also need to notice that at x equals -4, we actually has a local maximum at x equals -4 and also a local minimum at x equal to 0, but nothing. Okay, we have a vertical asymptote at x equals -2. Okay, now, so when you are writing down the final answer, so you say f is increasing on the interval from -infinity to -4 or from 0 to positive infinity. Now, on the AP exam, I guess you already noticed that they usually, when you're trying to write the intervals, that the function is decreasing. So they try to like combine these two intervals as a single one. So sometimes they will just give you the answer option saying that from -4 all the way to 0. Okay, so So they actually includes the like the vertical asymptote point. So I guess it's not perfect, but I don't like it that way. So for me, I still want to keep it in two separate intervals for the decreasing interval from -4 to -2 and -2 to 0. Okay. All right. Okay. So the next one is the optimization problem. Okay. So the next one is the optimization problem, finding the absolute maximum of a quantity. So an isosceles triangle has a vertex at the origin and its base parallel to the x-axis on the curve y equals 8 minus x squared. So when I draw this graph, let's draw this parabola. So this is a parabola that the base function being shifted, like reflected over the y-axis. So it's open downwards and then shifted up 8 units. So this is the parabola. It's still symmetrical about the y-axis. All right. So then now we have an isosceles triangle. The vertex, it's located at the origin. And then the two sides is touching the curve at some point. Okay, so these are the like the variable point. Okay, so let's say this is the point x and 8 minus x squared. So this is the an isosceles triangle. So we want to find the largest possible area of this triangle. Okay, now so think about, I don't need to find the entire triangle. If I could find the maximum, the largest possible triangle area of like on the positive side in the first quadrant, that means I'm still be able to find like what is the x value that gives me the largest area of this half of this triangle. Okay, so I'm going to set it up. Okay, based on that. So first of all, I'm going to write the equation for this half right angle triangle. So it's still going to be 1/2 base times the height. So what is the base of this triangle? So the base of this triangle, it's all about the x value, right? So from 0 to x, this is the base. So we have 1x, and then times the base. So the base of this triangle, the height of this triangle, it's the y coordinate. All right, so this is 8 minus x squared, and then times 1x. So divided by 2, that would be the area of this half, like this shaded triangle. Okay. All right, so I'm going to look at this. So let's find the critical number. So this time we are not finding the dA dt, but just finding the largest, the absolute maximum value of this function a. So we're going to differentiate it with respect to x. Okay, so finding the dA dx. So now to make it a little bit easier, this is not a complicated function. So maybe it's better I try not to use the product rule. I want to expand all the terms out. So multiply the x into the two terms here. So we have 8x minus x cubed. Okay, sometimes be flexible. So you don't need to always use the product rule or the quotient rule if you can do it easier, all right, by expanding the terms. So dA dt would be 1/2 times 8 minus 3x squared. That makes sense? Okay. So now to find the critical number, we know that we just need to make the dA dt equal to 0. So we are solving this equation, like when 8 minus 3x squared, it's equal to 0. So that means 3x squared, it's equal to 8, and x squared, it's equal to 8 over 3. And of course, x, it's going to be the square root of 8 over 3. And we only need to consider the positive square roots because we are looking for the positive square root of positive x value. Okay. All right. Now, if I look at this value, so square root of 8 is just 2. Oh, sorry, it's 2 root 2. So we're looking at 2 times the square root of 2 over the square root of 3. Okay, or you can write it as 2 times the square root of 2 over 3, or leave it like this, doesn't matter. Okay, all right, so now how can we convert, like proving this x value, the critical number is going to give me the absolute maximum? So there are two ways to go about it. You can use the first derivative test. Okay, using the first derivative test. So just as usual, you want to make sure that you're checking the sign of the dA dt. So you can use your calculator, figure out what is the approximate value of square root of 8 divided by 3, approximately equal to. So this number is approximately equal to 1.63. Okay, so you just check. All right. Using the test point. So let's say the x value it's 1 and then x equals 2 as a test point, and we are trying to test the sign of a prime or dA dx. Okay, so when you actually calculate these number, you would expect to get the a prime it's positive and then negative. So that means the a it's increasing and decreasing. Okay, it's strictly decreasing after this point to the right of this critical number. So this point here at x equals square root of 8 over 3 is not just a local maximum, it's actually an absolute maximum point. Okay, so the absolute maximum is going to occur at this critical number. Okay, now another way to prove this local maximum is actually an absolute maximum. We can use the second derivative test. Okay, because in this case, I can see that even though I use the second derivative test to prove this x value is going to give me the absolute maximum, it depends on the derivative function. So this is the derivative function. It's not very difficult if I need to find the second derivative. All right, so just think about the first term would be 0 and then minus 6x when you take the second derivative. Okay, so the first term would be 0 and then you have negative 3x. Yeah, oh, sorry, divided by 2. Yep. So that would be this. So think about when I substitute the x value into this function, I know that no matter what, this second derivative is always less than 0. So what does it mean when the second derivative of this function, it's always less than 0, okay, on its domain? That means the entire graph is going to be concave downward, right? So that means this point here at x equals square root of 8 over 3, it's always like it's going to be the absolute maximum point of the graph. Okay, so this is another way to like justify why this point, the local the critical number is not just give you the local maximum, but the absolute maximum of the function. Okay. Any questions so far? All right. Now, so the next question is another typical optimization problem. So, okay, let's read the questions together. A can is to be constructed in the shape of a cylinder. So draw a cylinder. Okay. And then so that the volume of the cylinder is 20 cubic meters. Okay, the tin at the ends, so at the two ends here, it's thicker than that for the sides. So therefore, the ends cost $2.50 per meter square, but the sides cost only $2 per meter square. So we want to determine the dimension of this cylinder that would minimize the cost as exact values. Okay, so we want to find the absolute minimum of a cost function. All right, so first of all, let's define the variable. So to talking about the volume, we need to know, we need to have two variables, two dimensions. Okay, the r, the radius, and also the height. Okay, so we know that the volume of this cylinder is all based on the base area times the height. Okay, so we can easily like express the h, the height, in terms of the radius. Okay, and now the second part, we're going to set up the quantity equation. That is going to be the cost. Okay, so first of all, let's look at the two ends. So it costs $2.50 per meter square for the two circles at the tops. So the area of the circle is 2 times pi r square, and then plus the psi. So we know that the psi, it's when you cut it up, it will become just like a rectangle. So you have two base, right, plus the two plus the psi. That would be $2 per meter square, and then the length would be 2 pi r, which is the circumference of the circle, and then this is still the height. Okay, the width of this rectangle is the height of the cylinder. So we have 2 times 2 pi r times h. Okay, so that is the quantity equation, but this one involves two different variables. So, but it's easier to fix it. We can substitute 20 over pi r square for h here. Okay, so now we can have the equation C as a function of r. So that would be 5 pi r square plus 4 pi r times 20 divided by pi r square. Okay, so let's simplify it before we differentiate it. So we have 5 pi r square, and then this one, we cancel the pi, we also cancel one of the r, we have 80 over r. Okay, so C prime. Okay, before we differentiate, maybe you also think about, oh, the r must be greater than 0. Okay, so y prime. So the first term, using the power rule, we have 5 pi times 2, that's 10 pi, and then r. Okay, second term, you can think about 80 over r is the same as 80 times r to the power of 1. So when you use the power rule, that would become negative 80 times r to the power of negative 2. So you can rewrite it in the denominator. Okay? All right, so now I'm going to like write this in a single term. So r squared is the common factor. So we have 10 pi r cubed minus 80. So this is the C prime of r. Okay? So now to find the critical numbers. So the critical number, okay, finding the 0 of the numerator. So that would be 10 pi r cubed equals 80. And then r cubed is equal to 80 divided by 10, that's a over pi. Okay, so r would be the cube root of 8 over pi. And we know that, oh, the cube root of 8 is a perfect cube number, so we have 2 over the cube root of pi. Okay, so that is the only critical numbers we have. So because the denominator, because r cannot be equal to 0, so we don't get any more the critical number. Okay, so now once again, we want to make sure that this r gives me the absolute minimum point. So you can also like quickly use the first derivative test to quickly show that this r, the critical number, is going to have the absolute minimum. So this number is roughly approximately equal to 1.365. Okay, so when I do the sign chart, 0, 1.365. Okay, so here I can use the test point r equals 1, r equals 2, So I'm just checking the sign. So just quickly calculate it. 10 pi r cubed minus 80. All right. So you would expect to have this number would be a negative, positive. So C prime of r would be negative, positive. So that means the cost would be decreasing and increasing. So we have actually an absolute minimum point occur at this r value, 2 over the cube root of pi. That makes sense? Okay. So of course, to finish up this question, you still need to find out the height. Okay, so when r equals to this number, then the height would be 20 divided by pi r squared. So I just give you the answer for this one. So the r would be 2 over the cube root of pi. Unit is in meters. And then the height would be, the exact value for the height would be 5 over the cube root of pi meters. Okay, so that would be the exact dimensions of this cylinder. Okay. All right. Okay. Next one. Am I going too fast? Okay, number 17. So number 17 is another interesting optimization problem. Okay, so a man in a boat on the river is 4 kilometers from the shore and wishes to go to a point on the shore 10 kilometers upstream along the strict shoreline. So let me draw the shoreline. So let's say from this point, okay? So let's say the man in the boat is here. So this is 4 kilometers. So this is the river, okay? And then this from here to here is 10 kilometers, okay? So this is the man in the boat, okay? All right. So now, so what happens here? So he can row his boat at this speed, okay, at this speed, 4 kilometers per hour, and also he could walk at this speed, 5 kilometers per hour. So to what point on the shore? So you're looking for like at what point on the shore that he should row to reach his destination as soon as possible. So as soon as possible means that the shortest time. You want to minimize the time, finding the absolute minimum time. Okay, finding the shortest time. Okay, to get to the destination here. So let's label the point. So let's say this is point A, this is point B, and then point C could be anywhere from this point B to this destination. So let's make a point C like somewhere in between. Okay, so let's say think about the situation that this man can actually choose to road straight ahead to point B and then walk all the way to point D. That's one option. Or he could actually row his boat all the way to the point D, to his destination, so that he doesn't need to walk at all. All right. Or he could choose to row his boat to reach the point C, and then get off the boat and walk along this shoreline to get point D. Okay. Now let's say I'm going to look at the situation that he is actually going from point A to C and then plus the point C to D. Okay, so this is the distance that he would choose to, the path that he's choosing. Okay, all right, so first of all, I'm going to look at, I need to find out the distance that he actually rowed his boat. from point A to C. So to find the distance, we need to know the speed and the time, right? Multiply the distance by the time to get the distance. All right. So in this case, if I need to introduce a variable. All right. So let's say I'm going to define x here. Okay. Let's say x represents the distance between the B and C, so that we know that the man has to walk for x minus x kilometers to get to the point D. Okay. And then this point, the length of the hypotenuse of this right angle triangle using the Pythagorean theorem would be just simply x squared plus 16. Okay. So now I'm going to set up the quantity equation representing the time. So the time it's always, the time it's always d divided by the speed. Okay, so now we're going to divide the distance. So let's say the first part, x squared plus 16, square root of x squared plus 16 is the distance for rolling the boat. And then the speed is 4 kilometers per hour. So this first expression represents the time it takes to get from point A to C on a boat. Okay, and then plus the second part, which is the walking distance, okay, which is 10 minus x, and then divided by the walking speed, which is 5. Okay, now in this case, I want to also think about what is this time, the function for the time, what is the restriction on the x, what is the interval? Can we define this function, the time function, on a closed interval? Yes, because remember we talked about there's two extreme option, that the man can go straight to point A, from point A to B, and then walk all the way to point C. In that case, then the x value actually has the lowest value. The smallest value for x would be 0. And then the second option is that the man can actually row his boat all the way from point A to D. That means the x value in this case would be 10. Okay? So yeah, so in this case we have the x value bounded by 0 and 10. So that means when we try to find the absolute minimum value of the time, then we can use the extreme value theorem approach, okay, to compare the time, the different times at the critical number and also at the endpoint. All right, now let's try to get through this, finding the derivative of this function. Okay, so time, so let's say t prime of x is equal to 1 over 4. So the derivative of the first term using the power rule would be 1/2 times x squared plus 16 to the power of negative 1/2, and then the chain rule, 2x. Okay, second term, we only have negative 1 over 5. Okay, so let me rewrite this, simplify this function. So 2 and 2 cancel, and we still have 4 times the square root of x squared plus 16, and then an x on the top. Okay, and then minus 1 over 5. Okay, so now to find the critical number, you can also combine it first, combining these two terms. So we have a common denominator, 20 times x square root of x squared plus 16. And then the first term we need to times it by 5. The second term we need to times it by 4 times the square root of x squared plus 16. So this is t prime of x. Okay, now to find the critical number, so the critical number would be when t prime of x is equal to 0. Okay, so we just need to look at the numerator when 5x minus 4 times the square root of x squared plus 16 equal to 0. So we are solving for x in this radical equation. Okay, so the best way to solve this equation is by squaring both sides. Okay, so we have 25x squared equals 16 times x squared plus 16. Okay, so remove the bracket. All right, so we have like 25x squared equals 16x squared plus 16 times 16, that's 256. So altogether we have 9x squared equals 256. So x squared equals 256 over 9. And x is supposed to be the positive square root of this. Okay? So that is the nice number. That would be 16 over 3. Okay?
I have a question.
Yes.
So when you were getting the critical number for t
Prime?
prime x, you don't. So we don't have to care about the one
In the denominator?
Yeah.
Okay, no, we still need to look at what if the t prime is undefined, right? So you follow through the definition for the critical number. Are we getting any like possible critical numbers when the t prime is undefined? So think about when the x squared plus 16 is has to be greater than 0, right? When it is undefined, that means you're looking for the number that is either less than or equal to 0. Is it possible to get any solution that is equal to 0 or less than 0?
No.
No, hey? So that means we don't get any critical numbers based on the 0 of the denominator.
Oh, okay.
Can you see it? Yeah,
Right.
that's correct.
Thank you.
You're welcome. That's a good point, right? You don't want to miss it. Sometimes, like usually in this case, the application problem, usually even though when you try to like look for the undefined the derivative function, so take a moment, you see, oh, even though we try to find the undefined value or the 0 of the denominator, we're not getting any solution. All right. So that's okay. All right. So this one is fine. So this is the only critical number we have, okay? X equals 16 over 3. And now, don't forget, we are using the closed interval, like the EVT method, to find out the time, okay? The absolute minimum value of the time function. So here, from 0 to 16 over 3, and also to 10, right? These are the only 3 x value you want to check the time, the function value. So when x is equal to 0, that means like when the man is going all the way, okay, to this point D. So that means he doesn't need to run at all. All right. So that means like you're looking at the function value of t. Okay. So try to plug in when x equal to 0. Okay, x equal to 0. You're looking at the first term would be square root of 16 divided by 4. That's 1 hour, right? Square root of 16 is 4. And 4 divided by 4 is 1. And then plus 10 minus 0 divided by 5, that is another 2 hour. So it takes like all the way 3 hours, okay, to complete this journey. Okay, and do the same thing when x is 16 over 3. Then we have the time for this one would be 2.6 hour. Okay, when x is 10, then it takes 2.69 hours. So now you can easily see that the shortest time, okay, so the man can get to the destination as soon as possible at the fastest way is when he could row his boat 16 over 3 kilometers. So this point here would be 16 over 3 kilometers. Okay, this part here. To get, that is the fastest path to get to the point D. That makes sense? Okay. So you can write this, the final statement, so saying that he should row to point C, okay, which is 16 over 3 kilometers from the point B. Okay? That makes sense? All right, so hopefully this few optimization problem and the related rates problem reminds you like the basic technique, how you solve these problems. Okay. So on the final exam, the written part, you would expect to get like one related rates problem, one optimization problem for sure. Okay. All right. So now chapter 5. So chapter 5, the first one, number 18, is all about the limit. So I'm going to let you try on your own. See, you can quickly figure out what would be the limit of the given function. Okay, for each part, for each question. So I'll give you 1 minute to see you can do it. Okay, who gets the first one? So what is the limit of 3 divided by x minus 2 as x approaching 2 from the left-hand side? So think about this number approaching 2 from the left-hand side means you're looking at x could be a number like 1.999999. Okay, so now you're looking at 3 divided by a negative small number very close to 0. So what kind of number you would expect to get? It's a negative infinity. Okay, so basically if this is a limit problem, then you can just simply say it does not exist. But if this is a function, the limit that you try to find, look for the information how the curve behaves as x gets near to the 2. Because of you want to sketch the graph, then you may want to like be more specific, knowing that the limit of this function is going to the negative infinity. Okay. All right. Part B. So can I ask Amarin, are you there? Amarin?
Yeah, I'm here.
So do you know how to do this one?
Would you factor out the denominator and then they cancel out?
Well, let's see, okay? Let's see if this is factorable. Okay. Yeah, it's factorable, positive, negative. So we do have a common factor, right? So that means the limit can be simplified to just 1 over x minus 2. But are we trying to find the POD? We know that this function, if you have to sketch the graph, we know that there's a POD at the point x equals negative 3. And in this limit, we are not interested about finding the y coordinate, right? So in this case, we just need to use the direct substitution, put x equals 3 back into the simplified form. Then we have the limit value. Yeah, that's correct. Okay, good job. All right. Now, if you want to find the POD, the y coordinate of the POD, then you actually need to take the limit as x approaching negative 3. Okay, instead of going to approaching 3 from the left hand side. So if that is the case, then you will have the POD, the coordinates of the y coordinates of this point, the POD would be at negative 3 and negative 1 over 5. Okay, so make sure that you understand what the limit would give you the information about the curve. Okay, how about C? Anyone gets the C? This one is easy. Okay, how about Hunter? Hunter? So what is
I'm writing it on a piece of paper and I have not
Oh.
finished writing it.
Okay. It must be tough for you writing down the limit. Okay, so what do you see? So this is a rational function, right? We're interested the end behavior, the right end, the right side of the curve, the far right side of the curve. So can you see that we have a horizontal asymptote on this curve when the degree are the same, right? When the degree are the same. So that means we are looking at a horizontal asymptote at 4, at y. So this is a horizontal asymptote at y equals 4. Okay, and that is also the limit value. That's equal to 4. Okay? All right. Now, how about D? So D is another rational function, but then this one, the degree in the numerator is 3, but then the degree of the denominator is just 2. So if you're interested about the horizontal asymptote, definitely this one doesn't have any horizontal asymptote. So basically you can say this limit does not exist. Okay, there's no limit at all. Okay. But if you look carefully at this function, if you trying to see, oh, I still want to look at if the function has any other asymptote. Okay, we know that this function doesn't have any vertical asymptote because the x squared plus 1, it's always greater than 0, right? We don't have any like non-permissible value. So this graph doesn't have any vertical asymptote, and this graph doesn't have any horizontal asymptote as well. But do we expect to get a slant asymptote on this curve? Yes, okay, this is something you need to remember, that when the degree of the numerator is 1 degree greater than the degree of the denominator, then you will expect the graph has a slant asymptote. Okay, so how do you find the equation of this slant asymptote? Remember, we use the long division. Okay, so let me show you this one more time. Okay, so dividing the numerator. So keep in mind this one has a missing term. The x term is missing. And then we are dividing it by x squared plus 1. Okay, so the first term, we need to times the x squared by 1x to get the first term. And then the second term, 1 plus x, we're going to put it down, the 1x like underneath the x term. And then think about the long division is subtract. Okay, so the first term get cancelled. We have 3x squared, bring it down. And then we have negative x minus 4. Okay, so repeat the procedure. We have to times it by x squared by 3 to get 3x squared. And then 1 times 3, it's positive 3. So subtract the 2 lines again. So we have negative x minus 0, that's still negative x, but then the constant term would be negative 7. Remember, this is the remainder. But the equation of the asymptote, it's all based on this, the quotient. So that means the equation would be y equals x plus 3. Okay? So that is the most quick and easy way to come up with the equation of the slant asymptote. Okay, using the long division. Yeah, that makes sense. Very good. Okay. All right. We almost we have 5 more minutes. So I guess we can stop at this time, at this point. So hopefully we are able to finish the rest of this review package in tomorrow's class. Okay. Are we all right so far? So don't be scared. The math final exam, the math 31 final exam is all about the strict forward question. So we are not testing something very difficult, just the basic concept. Okay. All right. So again, it's not you're writing this math final 31 final exam part 1, part 2 next Monday and Tuesday. Okay, during class. So I hope that you guys can get like 2 hours to do part A, the 30 multiple choice question, and also the 2 hours on the written response questions. Okay. All right. Go. I'm going to stop recording, and then you guys can ask your question if you like, if you have any. All right. Let me stop recording.